This is a video lesson for kinematics equations. The learning target for this lesson is, I am learning to use the kinematics equations to describe accelerated motion in one dimension. The success criteria for this lesson are, I can understand the variables in the kinematics equations, and I can use the kinematics equations to solve real-world problems. Alright, so what are the kinematics equations? We've looked at these in class before. So first, the equation of motion in one dimension. So this is for non-accelerated motion. This is for motion that is moving at a constant speed. So we have x equals x naught plus velocity plus vt. So x is the final position, x naught is the initial position, and then v is the velocity, and t is time. So again, this is motion that is moving at a constant speed, so the velocity is constant the entire time. When we have distance when undergoing constant acceleration, this equation gives us the change in position over time. So we have x is the final position, x naught is the initial position, v naught is the initial velocity, t is time, and then we have a, which is the acceleration, and then the time is squared. So again, this is when we have constant acceleration. Our velocity when undergoing constant acceleration. So we have v equals v naught plus acceleration plus at. So our final velocity is v, v naught is our initial velocity, a is our acceleration, and t is time. And then final velocity squared when undergoing constant acceleration. So we have v squared equals v naught squared plus 2a times x minus x naught. So this incorporates most of our variables except for time. So we have our final velocity squared is equal to our initial velocity squared plus 2 times the acceleration times our displacement, or x minus x naught. So that's our final position minus our initial position. So these are the kinematics equations that we're going to use over and over again in this class. Alright, so let's look at our first example problem. This is a range of position problem, and this is from AP. So we have at time equals 0 seconds and at time equals 2 seconds. A cart is at x equals 10 meters and has a velocity of 3 meters per second in the minus x direction. The cart has a constant acceleration, so using kinematics equations here, in the positive x direction with a magnitude of 3 meters per second squared is less than a, which is less than 6 meters per second squared. So we have a range of accelerations. Which of the following gives the possible range of the position of the cart at t equals 1 second? Okay, so we're looking for a possible range of positions. Okay, so what I'm going to do is I'm going to use this equation right here, and I'm going to plug in the time t equals 1 second, and I'm going to plug in this magnitude of acceleration at this time, and I'm going to use this as our initial position, and we're going to see what our positions come up with. Okay, so I'm going to use, so we say x is equal to 10 meters, and our initial velocity is 3 meters per second in the minus x direction. So we have minus 3 meters per second, and that's times time, which is 1 second, because we want to know what the range is between at 1 second. And then we have plus, we have times 1/2, so I'm going to write that as 0.5 times 3 meters per second squared times 1 second squared. Okay, so rewriting this, we have 10 meters minus 3 meters, and then this is 0.5 times 3 times 1 squared is plus 1.5 meters. So 10 minus 3 is 7, plus 1.5 is 8.5 meters. Okay, then I'm going to do the next one. So we have x is equal to 10 meters minus 3 meters per second times 1 second plus 0.5 times, and now our acceleration is this 6 meters per second squared. 6 meters per second squared times, again, 1 second, and that's squared. So we have 10 meters minus 3 meters plus, so 0.5 times 6 is 3 times 1 squared is, so 3 meters, and that's equal to 10 meters. So our range is 8.5 and 10, which is B. All right, so that's how you would solve this type of problem, or this problem specifically. All right, let's look at this example number 2, which is a gravitational field from a position time graph. So we have this position time graph here. So we have the vertical position on the y-axis, and this is in meters, and we have time in seconds on the x-axis. We have an object is released from rest, so our initial velocity is going to be 0. Near the surface of a planet, the vertical position of the object as a function of time is shown on the graph. All frictional forces are considered to be negligible, so we can ignore friction. The strength of the gravitational field is most nearly, so we're trying to find the gravitational field. All right, so I'm going to go ahead and move to the next slide so I have some room to do calculations. Okay, so here we are with all of our initial information. So from the graph, we know that our initial position is 300 meters. Our final position is 0 meters. Our initial velocity, because we were at rest, is 0 meters per second, and our time is 10 seconds. And then here are our answer choices. So I'm going to use this equation again, x equals x naught plus v naught t plus 1/2 at squared. Okay, so plugging stuff into the equation, so we have x is equal to x naught, which is 300 meters, plus our initial velocity is 0, so 0 meters per second, times time, which is 10 seconds. So this just goes to 0, plus 1/2. So I'm going to do 0.5 times our acceleration, which is what we're looking for. So I'm going to write this as a negative g. Where's my eraser? There we go. Okay. So I'm going to write that as minus 0.5. And then I'm going to write this as g, because that's what we're looking for, times t, which is 10 seconds, and then square that. Okay, so we have x is equal to 300 meters minus 0.5 g times 100 seconds squared. Okay, so I'm going to move all of this whole thing to the right side, so and do the multiplication. So we have 50 seconds squared, so that's 100 times 0.5 is equal to 300 meters. So divide both sides by 50, and we end up with, so let's see, so this should be 50 seconds squared times x. So we have x is equal to 6 meters per second squared, which is equivalent to 6 newtons per kilogram. So we're going to learn about these units, newtons, when we get to forces. All right, so our answer is B. All right, and that's how you solve a problem like this one. Okay, so what have we learned in this video? So we learned about the kinematics equations, what they are. So they're equations of constant accelerated motion. And we learned about using the kinematics equations to solve problems. So we learned which equations to use and how to set it up and solve it. All right, thanks everybody.